The solar system contains 8 planets, 9 if you still hold out for Pluto, and not a single one of them besides Earth would allow a human being to survive for more than a few minutes without a spacesuit, and in some cases not even a few seconds with one. Here is every way you would die on each planet, explained in full. Let's break this down. Mercury. Mercury was the planet nearest to the Sun and the smallest in the solar system. A world whose specific combination of extreme temperature, near total atmospheric absence, and radiation exposure created a death scenario that depended entirely on which side of the planet you were standing on at the moment you arrived. The daytime side of Mercury, the hemisphere facing the Sun, reached temperatures of up to 800 degrees Fahrenheit or approximately 430 degrees Celsius. If you died on the hot side, you would be burned to death in seconds, while asphyxiating and having all the water vaporize from your body. The 3 simultaneous processes, combustion from the surface temperature, asphyxiation from the complete absence of breathable atmosphere, and rapid desiccation as the water that constituted roughly 60% of your body mass boiled away, would produce a death that was total and essentially instantaneous. The specific sequence mattered to the physics of what was happening, even if the subjective experience would be too brief to register. The thermal energy from the surface would reach you before your lungs could complete a single breath cycle. The radiation from the Sun at Mercury's distance would penetrate any unprotected tissue, and the lack of atmospheric pressure, Mercury having essentially no atmosphere capable of providing pressure, would cause your body fluids to begin vaporizing through the same process that caused the moisture on your skin. The nighttime side of Mercury presented a death scenario whose speed was comparable but whose mechanism was the precise opposite. Mercury is, for all practical purposes, a vacuum and has barely any atmosphere to retain heat. Therefore, death on the cold side would involve temperatures plummeting to approximately minus 290 degrees Fahrenheit, or minus 180 degrees Celsius. The near absence of atmosphere meant there was no medium to conduct heat away from your body gradually. In normal cold environments on Earth, the air touching your skin conducted heat away from your body at a rate your metabolism could partially compensate for. On Mercury's night side, radiation was the primary heat transfer mechanism, and your body would radiate its internal heat into the vacuum with a speed that Earth-based cold weather survival intuition could not prepare you for. The extremity temperature swings from the hottest daytime surface temperatures in the inner solar system to some of the coldest nighttime temperatures of any rocky body. Across a distance of only a few thousand kilometers was the most extreme thermal gradient on any planetary surface in the solar system, communicating that Mercury's most distinctive property was not its proximity to the Sun, but the absence of the atmospheric buffer that every other inner solar system planet possessed in at least some form. Venus. Venus had about the same gravity as Earth. You would be very familiar walking around until you vaporized. The delivery of that assessment by astrophysicist Neil deGrasse Tyson communicated both the scientific precision and the visceral reality of Venus as a death scenario. The most Earth-like planet in terms of size, mass, and surface gravity was simultaneously the most hostile to human life of any planet in the solar system, and the familiarity of the gravitational sensation in the moments before death was the darkest specific irony available in planetary science. Venus's atmosphere exerted a pressure at its surface equivalent to approximately 90 times Earth's sea level atmospheric pressure, the equivalent of being 900 meters underwater in Earth's oceans, a depth at which the pressure alone would crush unprotected human tissue before any other hazard had time to operate. If you landed on Venus, this hot planet would crush you like a plastic bottle. It would be painful, but don't worry, it would only last 5 seconds. The crushing was the most immediate mechanical threat, but Venus did not rely on a single kill mechanism. The atmosphere that was crushing you was simultaneously composed of carbon dioxide with clouds of sulfuric acid, and the surface temperature was approximately 900 degrees Fahrenheit, or 465 degrees Celsius. Venus has about 90 times the atmospheric pressure of Earth, clouds composed of sulfuric acid droplets, and surface temperatures hot enough to melt lead. The sulfuric acid clouds were not at the surface but in the atmosphere above. A human being falling through the Venusian atmosphere before reaching the surface would encounter the acid cloud layer at an altitude of approximately 50 kilometers, where the temperature was cooler but the sulfuric acid concentration was high enough to dissolve organic tissue rapidly. The specific sequence of a Venus death was therefore acid dissolution in the cloud layer during descent, then increasing heat and pressure as the surface approached, then crushing and vaporization on contact with the surface, a layered death whose each stage was individually fatal and whose combination communicated why Venus, despite being Earth's closest planetary neighbor, was the most comprehensively hostile world in the solar system. Hit the like and subscribe button to see more videos like this. Leave a comment on your favorite planet. Let's get back into the video. Mars. Mars was the planet that humanity had most seriously considered visiting, the subject of more mission planning, more terraforming speculation, and more science fiction than any other solar system body. And the specific way it would kill an unprotected human was more nuanced than Venus or Mercury's immediate annihilation, which made it simultaneously less viscerally terrifying and more instructive about what human life on other worlds actually required. Mars is very cold, but the air is very thin, so the intensity of the cold won't be as biting as it might otherwise feel at that temperature on Earth. The atmospheric pressure on Mars was approximately 0.6% of Earth's sea level pressure, thin enough that it provided essentially no protection against radiation from the sun and no meaningful thermal insulation, but dense enough that the cold was conducted to your skin at a rate lower than a perfect vacuum would produce. The average surface temperature on Mars was approximately minus 60 degrees Celsius, with polar winter temperatures reaching minus 125 degrees Celsius and equatorial summer temperatures occasionally reaching a relatively mild minus 20 degrees. With some very warm clothing, you could probably walk around on Mars until you couldn't hold your breath any longer. The observation communicating that the cold, while fatal without protection, was not the primary immediate kill mechanism. The absence of oxygen was. Mars' atmosphere was 95% carbon dioxide with less than 0.2% oxygen, a concentration that was approximately 1/200th of what a human lung required to extract sufficient oxygen for consciousness. You would lose consciousness from hypoxia within approximately 15 seconds of taking your first breath. The carbon dioxide concentration additionally causing hypercapnia, the buildup of carbon dioxide in the blood, whose specific symptoms of confusion, panic, and cardiovascular distress would overlap with the hypoxic loss of consciousness in a way that was both physiologically precise and psychologically unpleasant. The radiation environment on Mars was the additional long-term threat that immediate death scenarios did not capture. Mars had no global magnetic field and a very thin atmosphere, meaning that cosmic radiation and solar particle events reach the surface at levels approximately 40 to 50 times higher than Earth's surface exposure, a chronic radiation dose that would be fatal to an unprotected human over months rather than seconds. Jupiter was the largest planet in the solar system. 1,300 Earths could fit inside it. And the death it offered a human visitor communicated that size in the most specific physical terms available. There is no solid ground on Jupiter, so you would simply fall through it until you were crushed under its intense pressure, and the specific details of the falling and the crushing were the most comprehensive in any planet's death scenario, because the distance you would fall before dying was genuinely extraordinary. Jupiter's atmosphere began where the gas density increased to the point of being meaningful. There was no definitive surface boundary, just an increasing density of hydrogen and helium with depth. And a human being entering Jupiter's atmosphere without protection would immediately begin freezing in the outer cloud layers where temperatures ranged around minus 166 degrees Fahrenheit. The cold was the first threat, but as you fell deeper, the pressure and temperature both increased dramatically. By the time you reached the level where atmospheric pressure was equivalent to Earth's sea level pressure, the temperature had already risen significantly from the outer cloud temperatures. Deeper still, the pressure reached tens of thousands of times Earth's atmospheric pressure, and the temperature had risen to thousands of degrees, the conditions under which hydrogen was no longer a gas but a liquid, and eventually a metallic conductor whose properties bore no resemblance to anything a human body had evolved to encounter. The pressure at the core of Jupiter is so high that it would be like having 160,000 cars stacked on top of each other all over your body. The specific image communicating the physical force of a pressure approximately 45 million times Earth's sea level atmospheric pressure. The human body would be compressed, then crushed. Then the constituent molecules themselves would be subjected to conditions under which normal atomic chemistry ceased to function. The Great Red Spot, Jupiter's iconic storm system, larger than Earth and sustained for at least 350 years, produced winds of approximately 400 miles per hour within its structure, meaning that a human body entering the storm region would be simultaneously frozen, bombarded by ammonia crystal hail, and subjected to wind speeds that would strip away any non-rigid material in seconds. Saturn. Saturn, like Jupiter, lacks a surface. Its atmosphere of hydrogen and helium would offer no oxygen to breathe, and with average temperatures of minus 178 degrees Celsius, a human would freeze almost instantly in the outer atmosphere before falling deeper toward conditions of increasing pressure and temperature that would complete the destruction that the cold had begun. The core of Saturn is thought to be around 15,000 degrees Fahrenheit, a temperature that placed it among the hottest objects in the solar system's interior, though the specific mechanism by which a human body would reach that temperature was the mechanism of progressive crushing and thermal compression rather than any conventional idea of reaching a hot surface. Saturn's rings, the most visually iconic feature of any planet in the solar system, composed of ice particles and rocky debris ranging from centimeter-scale grains to boulder-sized chunks, presented their own specific death scenario for anyone attempting to land on them rather than on the planet itself. The rings were not a solid surface, but a disk of orbiting particles, each following its own individual orbit, and a human attempting to land on the ring material would be subjected to hypervelocity impacts from the surrounding particles, whose orbital velocities relative to each other could produce impact energies comparable to rifle shots. Saturn also had a moon, Titan, whose specific properties made it the most interesting death scenario in the outer solar system. Titan had a thick nitrogen atmosphere with surface pressure 1.5 times Earth's and a surface temperature of minus 179 degrees Celsius, with lakes and rivers of liquid methane rather than liquid water. A human on Titan's surface would freeze in the methane environment while simultaneously asphyxiating in an atmosphere with no oxygen, the combination of extreme cold and chemical incompatibility being the most specifically alien death scenario in the entire solar system. Uranus. Uranus was an ice giant with an atmosphere of hydrogen, helium, and methane, offering no oxygen to breathe. A human exposed here would suffocate instantly, while the extreme cold would freeze the body almost immediately. Surface temperatures on Uranus could fall to minus 224 degrees Celsius, making it the coldest recorded temperature in the solar system, colder than Neptune despite Uranus being closer to the Sun, the internal heat deficiency that made Uranus the coldest planet being one of the most specific unsolved mysteries in planetary science. The methane in Uranus's atmosphere was what gave the planet its distinctive pale blue-green color, the methane absorbing red wavelengths of sunlight and reflecting the blue-green portion back. But the methane's visual contribution to Uranus's appearance was the planet's least significant property for a hypothetical human visitor, the asphyxiation from the absence of oxygen being more immediately fatal than anything else about the atmosphere's composition. Uranus rotated on its side. Its axial tilt of approximately 98 degrees meant that its poles experienced approximately 42 Earth years of continuous sunlight, followed by 42 Earth years of continuous darkness, the most extreme seasonal cycle of any planet in the solar system. A human falling into Uranus's atmosphere would freeze within seconds, the minus 224 degree temperature being colder than liquid nitrogen, which was cold enough to make biological tissue brittle and shatterable rather than simply frozen. The specific quality of the cold being a form of destruction rather than simply an absence of warmth. Neptune. Neptune's atmosphere, like Uranus, contained no oxygen and would cause instant suffocation, but its most lethal feature was its weather, with winds exceeding 2,000 kilometers per hour, faster than the speed of sound. The winds of Neptune were the fastest sustained winds of any planet in the solar system, the specific mechanism for their generation being related to the planet's internal heat, Neptune radiating 2.6 times more heat than it received from the Sun. The internal heat source driving the atmospheric circulation to velocities that produce sound barrier breaking wind speeds in an atmosphere where sound propagation was itself dramatically different from Earth's air. A human being entering Neptune's atmosphere at the top of the cloud layer would be simultaneously asphyxiating from the absence of oxygen and being subjected to wind forces whose speed translated to impact energy equivalent to a high-speed vehicle collision with every cubic meter of atmosphere encountered. The combination of the wind's mechanical destructive force and the minus 214 degrees Celsius temperature meant that the body would be subjected to rapid fragmentation by the wind while simultaneously being frozen. The wind erosion and the thermal destruction operating in concert rather than in sequence. Neptune's Great Dark Spot, a storm system observed by Voyager 2 in 1989 that had since changed significantly, was a vortex system whose wind speeds at its boundary were among the highest recorded in any planetary atmosphere. The storm's specific fluid dynamics producing a localized concentration of the planet's already extraordinary atmospheric violence. Pluto. Pluto was classified as a dwarf planet in 2006, but its specific death scenario was both straightforward and poignant given the decades-long debate about its status. The surface temperature on Pluto ranged from minus 233 degrees Celsius to minus 223 degrees Celsius. Temperatures that approached absolute zero, the theoretical minimum of thermal energy at which molecular motion ceased entirely. At these temperatures, nitrogen, which constituted the majority of Earth's breathable atmosphere, existed as a solid, the nitrogen ice plains of Tombog Regio being the most visually striking feature of the NASA New Horizons flyby images from 2015. A human standing on Pluto's surface without protection would experience multiple simultaneous deaths. The temperature would freeze all biological tissue within milliseconds, the atmospheric pressure of approximately 0.01. Earth atmospheres would result in explosive decompression, the same process that astronauts feared most about sudden depressurization, where dissolved gases in the blood formed bubbles in the tissues, and the composition of the thin atmosphere, primarily nitrogen with trace methane and carbon monoxide, provided no oxygen for any biological process. The complete darkness that characterized Pluto's environment for half of its 248-year orbit around the Sun, the deep outer solar system receiving sunlight at approximately 1,000th of Earth's surface intensity even at its closest approach, meant that a human visitor would be standing in a landscape where the Sun appeared as a bright star rather than as the warmth-providing disk it presented from Earth. The psychological dimension of that distance from the source of all terrestrial life being the death scenario's most specifically human element. You would be too far from home, in too much cold, for too long.